Welcome back, students. In this video segment, we will cover section 5.3, matrices for linear transformations. Okay, a couple of things first. First of all, this section is probably one of the most difficult sections for our semester. Second thing, it's a very, very long section, so you might want to take this lecture in segments. You may want to take it in a couple of sittings, and I'll make a recommendation of maybe a place to break, and then maybe you can start some homework and stuff. The next thing is that we need to take a look at a brief review of something that we studied earlier in our discussion of vector spaces. We need to take a look at a brief review of coordinates and coordinate vectors. Okay, it's not a very difficult concept, but we're going to be using this definition throughout this lecture. So let's start with a vector space. Let's let V be a vector space. A vector space, and let's say alpha equals the set of vectors, let's say v1, v2, all the way up to v sub n. Let's let alpha be a basis for V. Okay, now let's pick something out of V. So let's let V be in the vector space V. Okay, so that implies that V can be written as a linear combination, uniquely as a linear combination of these basis vectors from alpha. So V equals C1 V1 plus C2 V2 plus ... all the way up to Cn Vn. This is old news for us. Okay, the thing I want to review with you is the concept of coordinates of V and coordinate vector of V. So the coordinates of V relative to the basis alpha are just the coefficients C1, C2, all the way up to Cn. We also have the coordinate vector of V relative to the basis alpha. So relative to basis alpha, and that is designated by the brackets subscript alpha, and it's a column vector that contains as its entries the coordinates of V. Okay, keep in mind that the actual vector V doesn't have to be a vector from Rn. V can be in a very strange vector space V that has nothing to do with column vectors. However, the coordinate vector of V is a column vector. The coordinate vector of V relative to the basis alpha is in Rn. Okay, this is very important. I'm going to look at some examples. This definition is so important that I need to make sure that we completely understand this concept of coordinates and coordinate vectors. So, example. So let's say part A. Let V, the vector space V, be R2. Let the vector V, small v, equal the vector, column vector 3, 2. Okay, so the vector v, which is the vector 3, 2, can be written as, actually before I do that, I should identify the basis. Sorry about that. Getting ahead of myself. Let's see, let's let alpha be the standard basis vectors for R2. So let's let alpha equal the vectors E1 and E2. A special reminder, E1 is just the vector, column vector whose entries are 1 and 0, and E2 is the column vector whose entries are 0 and 1. Okay, so let's take that vector V again, vector 3, 2, and we can obviously write that as 3 times the vector 1, 0 plus 2 times the vector 0, 1, or 3 times E1 plus 2 times E2. This is very, very simple. So the coordinate vector of V with respect to the basis alpha is, well, to get that vector, we simply pick off the coefficients of the expansion of V in terms of the basis vectors. If you miss that, it's just 3, 2, the vector column vector whose entries are 3 and 2. Okay, so in this case, the coordinate vector with respect to the basis alpha is the same thing as the vector itself. Okay, this is not always the case. This is not always the case that the actual coordinate vector and the vector that we're starting out with are the same thing. Okay, so let's take a look at another example, part B of this example, say B. Let's still consider R2. Let's let capital V equal the vector space R2, but I want to consider a different basis. Let's let B, the basis beta rather, equal 1, 0 and 1, 1. And we won't prove that this is a basis. You can take my word for it. They're definitely linearly independent. They're not proportional. And actually, it pretty much did it. We have 2 vectors that are linearly independent in R2, so they're definitely, we have a theorem that says we don't have to show spanning. We automatically get spanning. So this is in fact a basis. Let's consider the same V, small v, 3, 2. Okay, so let's write the vector V in terms of the basis vectors from beta. So V, which is 3, 2. How do we do that? We've done this over and over and over again. In this case, I'm going to cut to the chase. It's 1 times 1, 0 plus 2 times 1, 1. We can verify that very, very quickly. If you multiply 1 times the vector 1, the vector whose components are 1 and 0, you just get 1 and 0. If you multiply 2 times the vector whose components are 1 and 1, you get 2 and 2. You add those 2 vectors, you get 3, 2. Okay, so what is the coordinate vector of B relative to the basis beta? To get that vector, all you do is you pick off the coefficients 1 and 2 and put them in a column vector. So in this case, the coordinate vector of V with respect to this basis beta is not the same as the original vector of V, which is 3, 2. Okay, so the coordinate vector of V with respect to the basis beta is the column vector 1, 2. Now let's take a look at a little more abstract example. So let's take a look at C. Let's let V, the vector space V, be the set of all polynomials of degree 2 or less. Let's let a specific vector v in there, in that vector space, be the vector negative 6x squared plus 2. And let's consider the basis vectors, the standard basis vectors. Ooh, goodness, my bracket looked horrible there. Had a lot of coffee, so my hands are kind of shaking a little bit. I drink a lot of coffee. I'm recording this very late at night, and I drink a lot of coffee late at night. I think I've said that before. Anyways, let's move on. So, I would like the coordinate vector of v relative to the basis alpha here. So let's do this. So this is very simple. The vector v is negative 6x squared plus 2, which can be written as negative 6 times x squared plus 0 times x plus 2 times 1. So the negative 6 is the coefficient of the basis vector x squared, 0 is the coefficient of the basis vector x, and 2 is the coefficient of the basis vector 1. So the coordinate vector of b relative to the basis alpha is the column vector negative 6, 0, 2. And again, notice that the coordinate vector is in R3, but the vectors themselves look like nothing from. The vectors in P2 look nothing like vectors from vectors in R3. Okay, but coordinate vectors are always column vectors. So no matter how abstract your vectors are in your vector space, the coordinate vectors are always column vectors. I keep saying that, but it's a real important thing through our long section 5.3, okay, which we haven't started yet. So I want to look at one more example, then we'll actually dig into section 5.3. So let's let v equal the kernel of the linear transformation T, where T takes, it's going to look really complicated, but it's not so bad. Where T is a linear transformation that takes T d2 negative infinity to infinity is a set of all twice differentiable functions on the whole real on the whole x-axis for all real numbers into the set of functions whose domain is negative infinity to positive infinity. So let's let v be the kernel of a specific linear transformation T, where T takes d2 to f by T of y equals y double prime plus y. Okay, so T takes a function that's twice differentiable, that you can differentiate twice, and takes its derivative, two derivatives, and then adds the original function. Okay, so remember, we have to remember what the kernel of a linear transformation is. So remember that the kernel of this linear transformation is everything that gets sent to 0. It's if you didn't get that, it's the set of all y in d2 negative infinity to infinity, such that T of y equals 0. Okay, or the set of all, it's going to get less and less fancy looking as we move on here. It's the set of all y in d2 negative infinity to infinity, such that y double prime plus y equals 0. So it should look really familiar. If you don't see it yet, it's just the set of all solutions. Set of all solutions to the differential equation, second order differential equation, y double prime plus y equals 0. Okay, but we need to write it in this fancy term because we're looking at vector spaces. So we're looking at coordinate vectors of vectors within vector spaces. Okay, so the kernel of a linear transformation is everything that gets sent to 0. In this case, it is the solutions to the second order differential equation. Okay, well, we happen to have a lot of information about the solutions to this differential equation. We looked at this in section 4.2, a very, very simple differential equation. Let's let the basis vectors for this vector space be cosine x and sine x. If you notice, our second order differential equation has a general solution, c1 cosine x plus c2 sine of x. Okay, so we can choose as our basis vectors cosine and sine, definitely linearly independent. We haven't talked about it much, but the dimension of the set of all solutions to the second order differential equation is 2. That wasn't important before. So since these two vectors, these two functions are linearly independent, they're not proportional, they form a basis. Okay, let's let a specific vector in this vector space be 4 cosine x plus 3 sine x. This is definitely a solution. Remember, all the solutions are c1 cosine x plus c2 sine x. Okay, so what is the coordinate vector of v relative to the basis alpha? It is the column vector 4, 3, which has nothing to do, this doesn't look anything like the solutions to this differential equation. Okay, but coordinate vectors are always column vectors, so we can associate a column vector with any vector from a finite dimensional vector space. Okay, so now we're gonna start our section 5.3, and again, it's a long section. You might want to cut it into pieces. One more thing about this section. Your author did an okay job of explaining this section. I do this section in a very different order, and I think it's a lot easier to understand my presentation of this section than it is to understand the author's presentation. He brings up some really high-powered theorems and stuff that I'm not even going to allude to. I suggest, and this is probably one of the very few times that I ever do this as a math professor, I suggest you use this lecture, this video lecture, as your text. And you don't have to refer to the text. I'm going to use the same examples that he does in text. I'm staying very close, but my explanations are better. I'm going to even say it that way. My explanations are better than his, I believe. He's very inconsistent with some of the notation, and I'll let you decide though. If my video lecture is not adequate for you, you can definitely refer to the text, but the order is going to be very, very different. Okay. So let's get started. Okay, in a previous lecture, we made a very powerful, extremely powerful statement about matrix transformations. Notice that I've underlined matrix transformations. The statement was that every linear transformation from Rn to Rm, not every linear transformation at all, just those that go from Rn to Rm, is a matrix transformation. Okay, and what that meant was that is there is an m by n matrix A such that T takes something from Rn, T of x equals Ax. Okay, or T takes the column vector from Rn, x1, x2, all the way up to xn, and multiplied by the matrix A, A1, 1, A12, all the way up to A1n, AM1, AM2, AMN, an m by n matrix, times x1, the column vector x1, all the way up to xn. Okay, every linear transformation from Rn to Rm can be written this way. And we saw that we could do that very easily. For example, if we let T be the matrix transformation from R2, let's say back into R2, by T takes x1, x2, and turns it into x1 plus 2x2, 3x1 plus 4x2. We saw that we could basically factor out the A. We saw that we could essentially, and very simply, with every linear transformation that we saw of this form, factor out as the A the coefficients 1, 2, 3, and 4 in this case, x1, x2. So here's a specific example for a matrix from R2 into R2. We would like a more systematic way of doing this than just essentially factoring out the matrix. We would like to do something like this. Let's say we're viewing this matrix as a transformation from R2. Let's say V equals R2 into W, in this case still R2, equals R2. And we have a specific basis, alpha, which is V1, 1, 0, V2, 0, 1, standard basis vectors. And let's say we view the range of this linear transformation also in R2 as having the same basis. We'll generalize to different bases, but the same basis, alpha, which is, let's see, W1 equals 1, 0, the same basis, and W2 equals 0, 1. Okay. So the idea the systematic way of finding this A, besides factoring the matrix into A times x1 and x2, is to see what the action is on the individual basis vectors. So let's take V1 and compute T of V1, and V2 and compute T of V2. Okay. So I know this is a drawn out version of the simple factoring, but we need a systematic way of doing this because we can't, not every matrix transformation not every linear transformation is a matrix transformation. So I'm developing a systematic way of doing this for any linear transformation. So T of V1 is T of 1, 0, and T of 1, 0 is 1, 3. I'm just going back to the original matrix transformation. T of 1, 0, if I let x1 equal 1 and x2 equals 0, I get the x2's cancel out or disappear and you get 1, 3. So let's see what the matrix transform, oops, back to black here. Let's see what the matrix transformation does to V2. Matrix transformation takes V2, which is 0, 1, and transforms it into 2, 4. Okay, now what I'd like to do is consider A as the matrix. This notation is going to look a little funny, but we'll get used to it. As the matrix consisting of the coordinate vector of T of V1 relative to the basis alpha and the coordinate vector of T of V2 with respect to the basis alpha. Okay, so the coordinate vector of T of V1 with respect to the standard basis alpha is just the same column vector 1, 3. It's not, remember, it's not always the case that we get the same column vector. We just happen to in this case. We'll see many more examples where the coordinate vectors are not the same. But the coordinate vector and the vector themselves are the same. So if we define A as the matrix consisting of the coordinate vectors, then we get, let's put them in, the coordinate vector of T of V1 with respect to alpha is 1, 3. And with respect to alpha, the coordinate vector of T of V2 is 2, 4. Okay, and again, it looks very, very strange to consider it this way, considering we could just factor the original matrix, but we're heading for a more general case. We're heading for a way where we can find matrices of transformations without having to rely on some sort of factoring. Now, to make things a little stranger, and I apologize for using that terminology, we're gonna call this matrix A. We're going to write it something. We're going to call it something different than the matrix A. We write A is this notation. So, we write bracket T, linear transformation, sub alpha, and superscript alpha. Okay, and we define this as the matrix of the linear transformation T with respect to the basis alpha. Okay, we're going this matrix is going to play a huge role for us in this section. For us, this is just a fancy way of defining the matrix A, which defines the linear transformation from R2 to R2, or more generally from Rn to Rm. Okay. All right. So bear with me. I know it seems a little strange, maybe a lot strange. But what if the linear transformation wasn't from R2 to R2? What if it was from R2 to some other vector space? In this case, in that case, the matrix would not be possibly written as a matrix transformation. Okay, so let's consider that next. So what if? Oops, back to black. What if T was from R2, say, into P2? Okay, by, let's say, T takes x1, x2, and turns it into 2x1x plus 3 x2. Okay, in this case, it would be impossible to write this vector as t of x equals ax, because a times x is going to be a matrix. A times x, a matrix A times column vector x is a matrix, and the elements in the range here are polynomials. if you're not sure about what's going on with this linear transformation, let's take a look for example, t of the column vector whose entries are 5 and 4 is 2 times 5 or 10x plus 3 times 4 is 12. How are you going to write the polynomial, or the polynomial 10x plus 12 as the result of a matrix times a column vector? It's impossible. It's impossible. The big point in this section, is that we can do something very similar to what we did in the last example. In some sense, every linear transformation from one vector space to another can be given by some sort of matrix multiplication. I haven't indicated that at all here, but this is going to be the case. For every matrix transformation can be written as the product of A times a matrix A times a column vector X. In some sense, every linear transformation can be. Okay, we have to be very careful with what that sense is. So let's sort of mimic what we did in the last example with this one. Let's sort of see if we can derive some sort of matrix that defines this linear transformation. Okay, so let's take a look at, let's say, the vector v as being R2 and with a basis alpha as being the standard basis vectors, the standard basis. V1 is 1, 0. V2 is 0, 1. Okay, and then let's take a look at the vector space W as P2. Remember, our linear transformation goes from R2 into P2, two very, very, very different vector spaces. Okay, so let's take a look at P2 with the standard basis for P2. We'll call that the basis beta. And the basis beta has, let's say, W1 as its vector, first vector, basis vector X, and W2 as 1. Again, the standard basis vectors for P2. Okay, and I said P2, I wrote P2, and it really should be P1. That's going to be an easy fix, but my bad here. P2 is a set of all polynomials of degree 2 or less. Okay, and I wanted P1. So I'm going to do this right in front of your eyes. It's going to be R2 to P1. That's all I'm changing as a subscript, and I apologize. Crud. I've got it all written incorrectly in my lecture notes too. Okay, we're going to, let's see anywhere else I did that. Watch your eyes, I'm going back up. That's okay. Okay, so at least I caught it fairly soon. I don't want to read. I've already recorded about 30 minutes of lecture. I don't want to redo this or edit. I'm just being lazy. Okay, so what we want to do is check out the action of the transformation on the vectors from V. Okay, so let's do that symbolically, like saying in this rectangle we have the vector space V. So V1 is the vector 1, 0. V2 is the vector 0, 1. And I want to check out what the action on the vectors V1 and V2 are. Okay, so I want to find T of V1 and I want to find T of V2. Okay, so let's do that. So T takes V1, which is 1, 0, and turns it into what? Well, T of X is, T of X1, X2 is 2X1 times x plus 3x2. So it's 2x1 plus 0, so 2x. But then I want to write that in terms of the basis vectors in W. So this is 2 times x, that's the first basis vector, W1, plus 0 times 1. In other words, it's 2 times W1 plus 0 times W2. So T of V1 is 2W1 plus 0W2. So the first thing we're doing here is we're finding out what the linear transformation does to the basis vectors in V, and then writing that result in terms of basis vectors in W. If you missed that, we still have another one to go here. So T of V2 is T of the vector 0, 1. Well, what's T of 0, 1? It's just 3. Okay, if you're not sure about that, here I'm going to highlight this in red here. I'm going up and highlighting our linear transformation. Okay, so T of x1, x2 is 2x1x plus 3 times x2. So in this case, if x1 is 0 and x2 is 1, we get 3. Okay, so that's what V2 gets turned into. It gets turned into the first degree polynomial 3. Now I want to write that in terms of the basis vectors in W. So that is clearly 0 times x plus 3 times 1, or 0W1 plus 3W2. I'll write that up here. 0W1 plus 3W2. Okay. So what I want to do is I want to find the coordinate vectors for T of V1 and T of V2. So the coordinate vector of T of V1 with respect to with respect to the basis vector, the basis beta, is the column vector 2, 0, and the coordinate vector of T of V2 with respect to beta is the column vector 0, 3. Okay, so notice that again the vectors in W are not column vectors, but their coordinate vectors are always. Okay, so what we're going to do is we're going to define the matrix of T with respect to the bases alpha and beta to be the matrix that's composed of the coordinate vectors of T of V1 with respect to beta and T of V2 with respect to beta. Okay, and I realize I said the name of this matrix without writing it. I'll write it in a minute. Okay, so this is the vector, the matrix 2, 0, whose columns are 2 and 0, and 0 and 3. And what we call this is the matrix of T, the matrix of the linear transformation with respect to alpha, bases alpha and beta, bases alpha and beta. Okay. So what does this bizarre new matrix do? What does the matrix of T with respect to bases alpha and beta do? Well, let's see exactly, let's cut to the chase here. You're going to see the reason for this, the main reason for this section happening now. The section goes on and on, but you'll see the main reason right now. Now, let V equal x1, x2. Just a typical vector in R2. Clearly, because it's by definition, T of V equals T of x1, x2, just by definition. What was it? 2x1x plus 3x2. 2x1x plus 3x2. That's the definition of our linear transformation. Okay, now look what happens when I compute a very special product. Let's compute the matrix of T with respect to bases alpha and beta, and let's multiply that by the coordinate vector of V with respect to alpha. Okay, well, we just found that the basis, the matrix of T with respect to the basis alpha and beta is this diagonal matrix, 2, 0, 0, 3. And what is the coordinate vector of V with respect to alpha? Well, if it's just a 2 by 1 column vector, it's just going to be the same vector. We get that luxury. And what happens when we multiply this out? What happens when we multiply this out? We get 2x1, the column vector, 2x1, 3x2. Okay, now that's not the matrix T of V. That's not the transformation T of V. What is it, though? This is nothing more than the coordinate vector of T of V with respect to the basis beta. Look at the coefficients of T of V. Look at the coefficients of T of V. They are 2x1. Oops. My parentheses didn't go around quite around the correct place here. Hang on a second. There we are. Oof, I got real lucky there. Okay. Okay. Times 1. Look at the coefficients of T of V with respect to the basis vectors beta. They're 2x1 and 3x2. So while multiplying this matrix of T with respect to bases alpha and beta times the coordinate vector of V with respect to alpha, that doesn't define the matrix. It defines the coordinates of the result. And this is going to be true in the general case. Not every matrix, not every linear transformation is a matrix transformation. But in this sense, every linear transformation can be found by some sort of multiplication of matrices. Okay, this is a very, very powerful result in STEM field mathematics. In STEM field math, we would like our computers to do our operations for us. And computers do very well with matrices. Unfortunately, not every linear transformation is a matrix transformation. But in some sense, every linear transformation can be reduced to some sort of matrix multiplication by coordinates. Okay, if this doesn't make sense, we've got a long way to go with this section, and it should probably reveal itself to you better as we go along. Okay, now we're gonna be starting the general definition of this matrix of T with respect to two bases. And this is where symbolically it gets a little rough, but the concept is going to be exactly the same as what happened in this last example. The concepts are exactly the same thing. So we're going to be looking at the general definition of the matrix of T with respect to two bases, alpha and beta. Okay. All right, so let's do this. First of all, let's start with a linear transformation. So let's let T take vector space V into vector space W be a linear transformation. Okay. Let's do this. Alpha composed of V1, V2, all the way up to V sub n be a basis for the vector space V, and let's let beta equal W1, W2, all the way up to Wm be a basis for W. Now notice what I did there is the subscripts on the bases for alpha and beta don't end at the same place. The V and W are vector spaces, but they don't have to be of the same dimension at all. Okay. We can go from, specifically, we can go from R3 to R15, or from R75 to R1 or R2. So the bases, the dimensions are different in general. Okay. So let's do a couple of things. Let's see what T does to the basis vectors. T does to the basis vectors in alpha. And after we do that, or along the way, let's express those values, T of V1, T of V2, all the way up to T of Vn in terms of the basis vectors in beta. Basis vectors in beta. Okay, so this is what we're going to be doing here. Oops, let me do a little neater here. Okay. Here's the vector space V. Here's the vector space W. We have a basis V1, V2, all the way up to Vn. We have a basis beta on this completely unrelated vector space W, W1, W2, all the way up to Wm, as in Mary. Okay, so I'm going to take V1, I'm going to find T of V1, and then I'm going to take that T of V1, which is now a vector in W, and write it in terms of the basis from W. So I'm going to write that as some A1 W1 plus A2 W2 plus ... A, what's the subscript? M W M. But I'm going to do that with each of the vectors V1 to Vn. Okay, I'm going to do that to each of the vectors V1 to Vn. Okay, so I'm going to have to adjust the subscripts, the A1 to AM, a little bit to accommodate that we have so many vectors V1 to Vn. So let's do that right now. Okay, let's see what the linear transformation does to the vector V1. It turns it into T of V1, and then we're going to write that in terms of the the basis vectors where that T of V1 lies. It lies in W now. So we're going to make it A1 W1, but not just A1 W1, it's going to be A11 W1 because we're talking about V1 plus A2 W2, but A21 W2. The second subscript tells us we're looking at V1. The first subscript tells us it's the coefficient of W2. So plus A3 W3, but we're talking about V1, plus dot 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 all the way up to AM for V1 WM. So T of V2 will be A1 W1, but it's A1 for V2 plus A2 W2, but we're talking about V2 plus A3 W3, but we're talking about V2 plus dot 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 plus AM WM, but we're talking about V2. That's a coefficient of the expansion for V2. And we keep doing this until we get to T of Vn, the action of T on the nth basis vector in alpha. Okay, it's going to be A1 W1, but we're talking about Vn now, plus A2 W2, so we increase the subscript on A because we're talking about Vn, 2, plus A3 W3, but we're talking about Vn, plus dot 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 plus AM WM, but we're talking about we're talking about Vn. Basis vector is Vn. Okay, so we got a lot of entries here. Okay, now what we're going to do is we're going to define the matrix. So define the matrix of T. The matrix of T with respect to bases alpha and beta. With respect to bases alpha and beta. And that's going to be symbolically bracket T subscript alpha superscript beta. And it is, now look at T of V1. Take the coordinates of T of V1, T of V1 above, and I'm putting a red arrow there, T of V1. Look at the coordinates, A11, A21, A31, etc. And I'm going to put them as the first column in this vector. Okay, so this is going to be A11. In fact, it's a little bit labor intensive, but I think I'll do it. I'll put in red A11, A21, A31, all the way up to AM1. Okay, now take a look at T of V2. Okay, let's highlight it in green, I guess. Here's T of V2. And let's take the coordinates of T of V2 and put them in the second column of this matrix of T with respect to bases alpha and beta. So we have A12, A22, A32, all the way up to AM2. Okay, and we'll continue this process until we get to, I guess we'll do blue, T of Vn. Let's take the coordinates of that vector and put them as the last column in this matrix we're defining, a matrix of T with respect to alpha and beta. Okay, so A1n, A2n, oops, let me, this marker's kind of thick here. Let me change, just go to a pen. Give me a second here. Okay, here we go. A1n, A2n, A3n, dot, 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 AMN. And what we have is an M by N matrix. We have an M by N matrix, which represents the matrix of T with respect to the bases alpha and beta. The matrix looks real complicated, but it's real easy to remember in a different form. That first column is nothing more than the coordinate vector, or contains the coordinates of the coordinate vector of T of V with respect to beta. The second column is the coordinates of T of V with respect to beta. So it's really simple to memorize the matrix of T with respect to the bases alpha and beta by looking at the matrix as just a whole bunch of columns of coordinates. Okay, and if you're still confused about this, it's not a big deal. Our next example is going to force us to look very carefully at what this matrix is, and what it's doing. Okay, now we have a special case. We have a special case. If T is from the vector space V into the same vector space V, we call that a linear operator, then the subscript and superscripts, of course, are going to be the same. Okay, and we call that matrix by a different name. It's the matrix. You can call it, I guess, the matrix of T with respect to the bases alpha and alpha, but we don't. We call it the matrix of T with respect to alpha. With respect to alpha. Okay. So, in our near future, we have a big result. Big result coming up. So I'm spilling the beans. I already did this in an earlier example. Big result coming up later. Probably in about 20, 30 minutes more into this lecture. The coordinates of T of V with respect to beta equals the matrix of T with respect to alpha and beta times the coordinate vector of V relative to the matrix alpha. Okay, if alpha equals beta, that is, if we're going from V to V, then the coordinates of T of V with respect to beta equal the matrix of T with respect to beta. Oops. I think we need to do this. Alpha. The matrix of T with respect to alpha times the coordinates of V with respect to alpha. Okay, so this is where we're headed with the most important result in the section. For right now, we need to concentrate on computing this matrix of T with respect to alpha and beta, because it's not a simple thing. It's conceptually not so bad, but it can be very difficult to compute. So we're going to practice with this. We're going to practice. Okay, I'm going to be working example 1 in your textbook, but I'm going to do a better job at it. Your author decides to use some subscript, some notation that he's not consistent with. I'm going to be very consistent with the notation presented in the lecture so far. Okay, so if you want to read your textbook on this example, it's okay too. It's about the same, but I think I do a little better job. Actually, I think I do a much better job. Okay, so example 1. Example 1. Let's let T be a transformation that goes from R3 and goes back into R3 by T of XYZ, or X1, X2, X3 if you want to do that, equals I'm going to copy this very precisely. 5x plus z, 3x plus 2y minus 3z, and 5x. Okay, so clearly it takes a point in R3 and or a vector in R3 and produces another vector in R3. Okay, I want to consider two bases. Okay, so I want to consider the basis alpha as the standard basis for R3. So it contains the standard basis vectors 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. Otherwise known as I, J, and K in physics and calculus 3. Okay, but we're going to let beta be the base, a different basis. Beta has the vector, basis vectors V1, C1, 1, 2, V2 is 1, negative 1, 1, and V3 is 1, 1, 1. Okay. All right, so I want to find some stuff. So first, part A, find the matrix of T with respect to alpha. Okay, and that's nothing more than, yeah, my bracket looks really ugly there. The 3 by 3 matrix whose columns are given by T of E1 with respect to alpha, T of E2 with respect to alpha, T of E3 with respect to alpha. Just definition that we had about 3 or 4 minutes ago. Okay. So the first thing we need to do is figure out the action of the transformation on the standard basis vectors and write them in terms of the standard basis vectors. We want to find the action of the vectors on the basis alpha and then write those in terms of the basis in the other space, which is still alpha. Okay, if you missed that, just watch. Okay, so it's actually very easy for this. This is one of the easiest things to do here. So let's find T. Let's find the action on E1. T of E1. T of E1 is T of 1, 0, 0. Okay, now T of 1, 0, 0. Just look at our linear transformation above. I'll highlight it in red for us, just so we can look at it. Our linear transformation, there it is. Okay, so T of 1, 0, 0. So put x equals 1, y and z equals 0. So we get 5, 3, 5. Okay, we get the column vector 5, 3, 5. Okay, 5, 3, 5. Okay, now let's write 5, 3, 5 vector in terms of the vectors in the basis alpha, which is very, very simple. This is just 5 times vector 1, 0, 0 plus 3 times the vector 0, 1, 0 plus 5 times the vector 0, 0, 1. Okay, and we got to do the same thing with the other two vectors, the two vectors in alpha. T of E2, the action of T of E2, we'll do it a little more quickly, is T of 0, 1, 0. And T of 0, 1, 0, if you want to check, you can. This is 0, 2, and 0. Okay, so this, in terms of the standard basis vectors alpha, is 0, E1 plus 2, E2 plus 0, E3. Finally, the action on the vector E3 is T of E3. So it's T of 0, 0, 1. T of 0, 0, 1 is 1, negative 3, 0. Okay, if you're not sure about that, go back to the red definition of our linear transformation. Let x and y both be 0. Let z equal 1. Okay, so we get 1, negative 3, and 0. Okay, now write that result in terms of the vectors in the second space, the basis vectors in the second space, which are still alpha again. So this is 1, E1 minus 3, E2 plus 0, E3. Okay, so this is a simple thing here. The matrix of T with respect to alpha then is nothing more than, once again, it's T of E1, the coordinates, T of E1, T of E2, T of E3. So it's the matrix whose columns are the coordinates of the transformed vectors, basis vectors. Okay, so pick off the coordinates. The coordinates are 5, 3, and 5, column-wise. 0, 2, and 0. And 1, negative 3, and 0. Okay. And notice how simple that was. And I don't mean to be sarcastic. But notice how simple it was to find the matrix of a linear transformation with respect to standard basis vectors. This is a powerful result that it's simple with when we try to compute the matrix of a transformation with respect to standard basis vectors. It's very, very simple. It's not so simple when your basis vectors are not standard basis vectors, and this is what we're going to see now. Okay, so part B is quite a bit more complicated. Okay, so for part B, I want to find the matrix of T with respect to the basis vectors beta, basis beta. Okay, well, this is still nothing more than the matrix composed of the columns whose entries are the coordinates of the transformed basis vectors, T of V1 with respect to beta, T of V2 with respect to beta, and T of V3 with respect to beta. Okay, and these aren't so simple. These coordinates are not so simple. Let's dig in. Well, we have to remember what our basis vectors from beta were. So I'm gonna stop the video for a second and copy and paste them where we can use them here. Okay, I'll be back in a second. So here's our reminder. Here are the basis vectors beta. So what we want to do is systematically look at what the linear transformation does to each of these basis vectors, find some result, find T of V1, which is going to be some column vector, and then write that result in terms of the basis vectors V1, V2, and V3. Okay, so if you're not with me, just let's just do it. So we find T of V1. T of V1 is T of the column vector 1, 1, 2. Okay, if you take in and put into our linear transformation 1, 1, and 2, you get, and it's very easy to compute, you get 7, negative 1, and 5. So that's what the action is by the linear transformation on V1. Okay, now I want to write that vector in terms of V1, V2, and V3. So this is where your author uses some poor subscripts. He uses C1, C2, and C3. And that's not a good idea because we've used subscripts, we've used the variables A with double subscripts before. So this is very confusing for him to do C1, C2, and C3. So this is, in terms of the basis vectors from beta, this is A1, 1, V1 plus A2, V2, but it's A2 for V1, V2 plus A3, 1, V3. Okay. Okay. Well, I'm going to take V1, V2, and V3 out of there and put their actual values. Okay, so this is A11 times V1, 1, 1, 2, A21 times V2, 1, negative 1, 1, and A31 times V3, which is 1, 1, 1. And we do this with each of the basis vectors V1, V2, and V3. Okay, so let's do that. So T of V2 is T of 1, negative 1, and 1. Plugging in 1, negative 1, and 1 into our linear transformation. Maybe you ought to try it. You can always stop the video and do it. Just you need to be clear what's going on here. Okay, so there's no rush. Okay, so we're going to write those in terms of the basis vectors from beta. So this is A1 V1 plus A2 V2 plus A3 V3, but it's got to have a double subscript to indicate that we're doing this for V2. So it's A1 2 V1 plus A2 2 V2 plus A3 2 V3. And we'll move this along a little bit. We're going to do the same thing for V3. T of V3 is T of 1, 1, 1. Substituting 1, 1, 1 into our linear transformation, we get 6, 2, and 5. And we write that result in terms of the basis vectors from beta. So this is A1 V1 plus A2 V2 plus A3 V3. But it's not just A1 V1, it's A1 for V3. So A1 3 V1 plus A2 3 V2 plus A3 3 V3. Okay. Now focus now in what I have the brackets on here. This is 3 systems of 3 equations and 3 unknowns. Okay, so we need to solve these 3 systems for all these A11 through A33. Now there's a little bit of a shining light at the end of this tunnel. I'm going to write out these systems. Okay, we really need to see them, but there's something interesting about these systems that it's going to make things not so bad. So just give me a second. I'm going to write these systems out. So the first system will be concentrating on the first equation, A11 plus A21 plus A31. So A11 plus A21 plus A31 needs to equal 7. Okay. At some point, I'll stop the video and write out the other 2 systems, so you don't have to watch this for each system. Still focusing on the first vector equation. So we have A11 minus A21 plus A31 equals -1. And finally 2A1. Oops. That's okay. This is fine. 2A11 plus A21 plus A31. Let's see if I got that right. Yes. So much going on. Equals 5. There's the first system. Now I'm going to write out the second and third systems off camera. We're just going to look at we're just going to look at the next two vector equations. We have three systems of three equations and three unknowns. Okay, so give me a second. Almost literally, I'll reboot. Okay, so what I did off camera was to color coordinate things a little bit to make things really, really clear. We have those three systems of equations, each of which has three variables and three equations and three unknowns. Okay, and all the variables in each of the different systems are different. In the first system, you have A11, A21, and A31. Second one, A12, A22, and 32, A32. In the third system, which has green coefficients, A13, A23, and A33. All those variables are different in the different systems. However, what is the same in all three systems? They all have the same coefficient matrix. Okay? All three systems have different variables, but they have the same coefficient matrix. So if you were to apply the Gauss-Jordan elimination method to any of the system, let me start again. The Gauss-Jordan elimination method, the steps would be exactly the same for all three systems. Okay, now we could separately solve these systems using a calculator, finding the RREF in each case, or we could super augment a matrix to solve all three at the same time. Okay, if you miss that, we can solve all three of these systems at once. All three of the systems, while they have different variables, they have the same coefficient matrix. So what I could do is write one coefficient matrix, even though all the variables are different in the three systems. 1, 1, 1. And then augment that matrix with 7, -1, 5, 6, -2, 5, and in green, I'll go to green here, 6, 2, and 5, and let the calculator solve all three systems at once by finding the RREF of this 3 by 3, 6, 1, 2, 3, 4, 5, 6, 3 by 6 matrix. Okay. The elementary row operations for each of the three systems would be identical. So I'll solve all three at once. Okay, this is a really good thing here. So this is 1, 0, 0. After we compute the RREF, oops. I don't want to go to 1 in that column. 0, 0, 1. We end up getting the matrix, and I'm going to carefully copy this from my notes. God help me if I miscopied from my calculator. Let's see. 5. Okay. So that matrix that appears, the 3 by 3 matrix that appears in the right hand portion of this RREF, that is our goal. That is the matrix of T with respect to the basis beta, and we just pick off that matrix: -2, 4, 5, -1, 4, and 3, and -1, 2, and 5. Column wise. Okay, but notice when our basis vectors are not the standard basis vectors, it's not simple to find the matrix of a transformation. Okay. We have one more part to this. I want to find the matrix of T with respect to bases alpha and beta. Find the matrix of T with respect to the bases alpha and beta. So I'm going to go up and copy and paste the two bases that we need, and I'll be back in a second. Okay, so here are our two bases, sets of bases, and here's sort of a diagram of what we need to do. Okay, we want the matrix of T with respect to the bases alpha and beta. So what that means is our linear transformation is going from R3 to R3. So V equals R3, W equals R3. We need to take E1 and figure out what the action of the linear transformation is on E1. That means we need to find T of E1. Then we need to write T of E1 in terms of the basis vectors beta. So we're looking at the basis in the transformed space. The basis is beta, and the original space where we're starting our transformation from is the basis alpha. So let's do this. We first find T of E1. T of E1 is 535. It's still the same T of E1 we saw in part A of this. It's T of 1, 0, 0, which is 535, column vector. Now we write that in terms of the basis vectors beta. So it's A1 V1 plus A2 V2 plus A3 V3. But we need double subscript because we're dealing with E1. So it's A1 for E1 times the first basis vector, 1, 1, V1, 1, 1, 2, plus A2 1, 1, negative 1, 1, plus A3 1, 1, 1, 1. And we do that for E2 and E3. Figure out the action on E2. It's nothing more than T of 0, 0, 1, 0, which we figured out was 0, 2, 0 earlier. Just plug in 0, 1, and 0 into our transformation. So this is now A1, 2, first vector in beta, plus A2, 2, second basis vector in beta, plus A3, 2, third basis vector in beta. Finally, T of E3 is T of 0, 0, 1. Plugging into our linear transformation, we get 1, negative 3, and 0. And this is A1 V1 plus A2 V2 plus A3 V3, but for E3. So it's A1 3 V1 plus A2 3 V2 plus A3 3 V3. This is three systems. Each of these equations is a one system of equations. So we have three systems of three equations, three unknowns. The coefficient matrix for each of the three systems is identical, so solve all three simultaneously. The coefficient matrix is going to be 1, 1, 2, 1, negative 1, 1, 1, 1, 1. So this is cool. The super augmented part is 5, 3, 5, the constants for each of the systems. 0, 0, and 1, negative 3, and 0. I found the RREF. 1, 0, 0, 0, 1, 0, 0, 0, 1. And it was column-wise 0, 0, negative 1, 1, negative 1, and 2, and 4, 1, and 0. So the 3 by 3 matrix on the right, that is the matrix we're looking for. That is the matrix. This is the matrix of T with respect to the bases alpha and beta. Okay, so that is our goal. And it wasn't easy. It wasn't easy at all. Okay. Notice how hard steps B and C were. They were difficult because we weren't dealing with the standard basis vector transformation between using the standard basis vectors. We're going to return to this concept later in the lecture. There's a way of getting around having to compute the complicated matrix transformation by using the transformation between the transformation just involving the standard basis vectors. Okay, that's the second big result. Again, I want to stay with the big result for this portion of the lecture, though. I basically stated it, but I want to be more formal about it. This is from our textbook, Theorem 5.14. Suppose that T is a linear transformation between two vector spaces V and W. So suppose T is a linear transformation, let's see, how does this go? Let's see, let alpha be a basis for V and beta be a basis for the transform space, the codomain. Okay. Now here's the big result. If V is in the vector space V, this is the huge result for this section. This is not a matrix transformation. These vector spaces could be very, very abstract, non-matrix vector spaces. However, the coordinates of T of V with respect to the basis V equal the matrix of T with respect to the bases alpha and beta, not times V, but times the coordinates of V with respect to alpha. So it's very similar to T of X equals AX. Okay, very, very similar. It's not exactly the same thing. In fact, it's not nearly exactly the same thing because these are coordinates and not vectors themselves. However, once we know the coordinates of T of V with respect to the basis vectors, we just find T of V by putting in those coordinates as a linear combination of the basis vectors in beta, or basis vectors beta. If you missed that, that's what our last example is. Our last example is example 5 from your text. Last example that has to do with this result. By the way, I've decided to cut this video lecture into two separate video lectures. So we're going to do this one last example, example 5. Then we'll call this part 1 of section 5.3. And I'll label that in the title of the video. Then we'll actually do a part 2 to this, which should take another 45 minutes to an hour, I would imagine. Okay, example 5 from our text. This is to illustrate what this main result is for. Let T from R3 to R3 be the linear transformation from our last example. Okay, I'll write that out. Okay, so let T be the linear transformation from example 1, and I copied it there. We're also going to be using the basis beta that we've been using in our last couple of examples. Part A. So part A, find the coordinate vector of V relative to the basis beta. Okay, if, let's say, V is the vector 1, 2, 3, column vector 1, 2, 3. Okay, this is old news for us. This is old news. So I need to write the vector 1, 2, 3 is a linear combination of the basis vectors in beta. So let's just do it. 1, 2, 3. Again, this is old news for us. So this is nothing more than 1, 2, 3 is C1 times 1, 1, 2 plus C2 times 1, negative 1, 1 plus C3 times 1, 1, 1. Okay. This results in a system of equations. C1 plus C2 plus C3 equals 1. C1 minus C2 plus C3 equals 2. No double subscripts here. We're just looking for one set of constants. 2C1 plus C2 plus C3 equals 3. Okay. So the procedure, you use the Gauss-Jordan elimination method. I'm going through this part very quickly because it's something we've done so often in this course. It's probably automatic to you right now. So I put that into my calculator. I found the RREF was the identity matrix on the left. And what was on the right here? 2, negative 1/2, and I can't read my own writing for the last one. Negative 1/2 again. Okay, so that says that C1 equals 2, C2 equals negative 1/2, and C3 also negative 1/2. Okay. So that tells us what our coordinates are. The coordinate vector of V relative to the basis beta is the column vector 2, negative 1/2, and negative 1/2. That's not the vector V. That's the coordinates of V, the vector V, relative to the basis beta. So if you wanted V, you'd have to multiply 2 times V1 plus negative 1/2 times V2 plus negative 1/2 times V3, and you'd get V back again. Okay, so part B is what's going to illustrate what we just did. Find the coordinates of T of V relative to the basis beta. Okay, well, our big result is that the coordinates of T of V relative to the basis beta is equal to the matrix of T with respect to beta times the coordinate vector of V relative to the basis beta. Okay, now it's not going to look like there's a lot of work because we did all of that work. We did a ton of work for that matrix of T with respect to beta. So I'm just copying it now. We did this, and it's not as simple as just writing it out. Remember, we spent a lot of work on that. We did a lot of work on that. Okay, so I'm just copying that down, and then times the coordinate vector of V relative to the basis beta. And all this is work that a computer does. Even though this is a matrix transformation, if this had not been a matrix transformation, all of these quantities would still be matrices because they're just coordinate vectors. They're coordinates, rather, involving coordinates, okay, which are column vectors. Okay, and the matrix of T with respect to basis alpha and beta is just a matrix. Okay. Okay. So we get this result. So part C is going to seem silly. Find T of V. It may not seem silly at first, but I'll show you why it's going to look pretty silly. T of V is very simple now. We know the coordinates of t of, we know the coordinates of t of v. We just found them with respect to the basis vectors beta. So t of v is just pick off the coordinates. -3 times the first basis vector, way up top, 1, 1, 2, 1, 1, 2, second coordinate times v2, third coordinate times v3, should have memorized them, 1, -1, 1, and 1, 1, 1. Okay, got it. Look at all that work just to find t of v. Well, when you do all this matrix arithmetic, you end up with 8, -2, and 5. Not real exciting. And the thing that really makes it kind of silly out of context, I'll put this in context, is that's a lot of work just for finding t of v. Why don't I just find t of v directly? We could have just found t of v directly. I'm going to write this in red. We could have found t of v. V was just 1, 2, 3. So t of v, 1, 2, 3, directly. It would have taken us seconds. So what's the big point? Okay, I'm going to write out the big point, and I'm going to read it. Okay, give me a second. Oh my goodness, I realized I didn't pause the video. You're watching me do it. And I'm not going to edit this out. I apologize. Oh my goodness. That's embarrassing. Okay. Okay, so we could have found T of 1, 2, 3 directly. You've probably read through this. You're probably really pissed that I didn't pause the video here. The point is that linear transformations are not always matrix transformations, but this way of finding T of V by way of coordinate vectors allows us to make all computations matrix computations, regardless of the vector spaces involved. In part 2, coming up in the next part, we will look at an alternate way to compute this matrix of T with respect to beta. And as I was going to write before I noticed that I hadn't pushed pause, notice how easy it was. To find the matrix of T with respect to alpha when alpha was the standard basis vector, the set of standard basis vectors, the standard basis. We would like a way of computing. We want a way of computing the complicated one, the matrix of T with respect to a complicated basis, let's say, without ever having to look at that complicated basis, or not directly. We'd like a way to compute the matrix of T with respect to beta using the matrix of T, the easy one. And that's what we're going to do. Once again, I apologize for the lag there. It's probably a 3 to 5 minute lag. And I'll try to be more careful with pushing the pause button when I really want to pause. In any case, that ends part 1 of our video lecture, and I'm looking forward to talking with you all again in part 2 of section 5.3. So I'm going to push the stop button now. I promise.